Did folks get through homework too? There were question 1 and 3. I wasn't sure. I did a little bit of reinterpretation of questions 2 and 4. 4 is obviously the same as the collab 3. So I changed it around a little bit for myself. Instead of creating the layers myself, I just chose the layers from PyGeometry. And question 4 is a little more than the collab. It asks you to do node classification and graph classification on the 2 different data sets. So I did both, and there is a little bit of change for the graph data set. You basically have to, pool the graph embeddings into a single vector before you pass it in to the forward. So that's, and for the question 2, they talked about transy, and they were asking a bunch of theoretical questions. So I did it 2 ways. First off, I used the PyKeen package that I pointed out, and generated transy embeddings for a particular data set. I think it's called Freebase 15K or something. And it's a package thing. It's part of PyKeen. And then I use the same data set to, basically, create a network and learn the transy embedding by gradient descent. So I did the 2 things, and my loss curve in the PyKeen side, I ran 50 epochs of training, and the loss curve is much nicer on the PyKeen side. But so the metric was hit set 10. So the hit set 10 actually, I think, are comparable on both. So anyway, so that was my thing, but I didn't get a chance to do 1 and 3. 1 and 3 seems, 1 is about belief propagation, and it's kind of similar to the label propagation algorithm. And the other one is about something else, I forget now. Has anyone done anything?
I sort of done half of the first one, which is more kind of, it's more, if I remember correctly, more like, as you say, it's going back to belief propagation and calculating it more like manually.
Right, yeah.
In double codes. And then, I sort of started on question 4, but then I was working on collab 3, so I didn't really get around to finishing that. And then for C, I just, I haven't quite figured out how best to practice the knowledge graph stuff, because as you say, I don't necessarily want to do the derivations.
Exactly, right, yeah. Yeah, so, but the PyKeen package is actually very cool. It's got a whole bunch of built-in these embeddings, and basically they give you a training loop that you can just call on the model and the optimizer. Sorry, I interrupted someone.
No, I was asking on that only. I think you have mentioned this in the
Slack channel.
Slack channel. I'm just looking at, trying to search that. Sorry, I think I missed that.
This was yesterday.
PyKeen in the just at 9:14 yesterday. Yeah. Right. So I'm still to reach there. I'm still in collab 2 and 3, trying to finish it and doing the catch-up part, which I missed. I'm not still updated yet.
Okay.
Maybe we can have a maybe we can have a discussion on the previous chapters we were supposed to do. So if someone can share the screen, and maybe we can slightly go over that. Right now, what I understand is most of the fundamental part is covered now. It's more advanced additions to whatever the fundamental model is. That's
Yes.
my understanding. I could be wrong. So if we can have a review of that, then I'm still to reach at that level. Like I think chapter 15 or lesson 15 or 16 is right now or supposed to be done for this week, right?
I think 16, 17 was
16,
this week.
17. So I'm still like I'm at least 4 lessons behind.
Okay.
I'm taking my time to go through that and absorb it. So becoming more and more
Right,
complex.
right. Yeah, I'm actually going through in the opposite direction. I'm trying to get as much in, but again, with limited success, obviously. But
Okay, yeah, that's pretty humble of you. I think you are the one who have finished everything.
no. But the lectures, right? The 16, 17. It's actually the first one was, I think, to do with feature extraction, and that I thought was quite interesting. But I don't remember, so because I go through it so fast, I don't actually remember details. So I have to go back and I know where it is, like so that's my thing. I can always go back to it. So that's kind of like almost like a table of contents in my head. Okay. Okay. I can go through that 16, 17.
Yeah, that would be really helpful.
Okay. 16, 17, 1, 15, 4. Okay. So maybe 16. And should I? Oh,
Yes,
so, yeah,
saying
so,
something.
no. So this was I don't have actual notes, so I was
Okay.
just watching the video a little bit and just to refresh what they're talking about. So lecture 16 is basically saying that if so, how do you know that a node in a graph is isomorphic to a node in another graph, right? Just by looking at its neighbors is not enough, because he gives you a triangle and a square example, and a point on the vertex of either one. Both have 2 incoming edges, and but so you cannot distinguish just by looking at that, right? So then he suggests different ways. One of them is like I think positional. Then there is the anchor sets, and then there is something else. So anchor sets, I think they randomly select some nodes in the graph, and you basically find a vector so you said, let's say you select like 5 nodes randomly in the graph, and for each node you basically calculate the distance from the node to each of the 5, right? And so that's your vector describing the node. And so he went through these different embedding schemes. And I don't actually remember all the details, but this is like the gist of the lecture 16, like basically different embedding schemes to figure out, solve the problem of node isomorphism.
So shall I share my screen? Like I have the slides on my.
Yeah. Oh, you have slides. Okay, sure. Yeah, let's do that.
So, just a second. Share.
Oh, actually, I should have slides too. Yeah, okay.
Is this the one, right? 16th one.
Yes.
Okay.
Was there a video that went along with this? I was trying to coordinate between the decks in one place and the videos on YouTube. They seemed a little bit out of sync.
The videos are they have a lecture number, 16.1, 16.2, right? So I basically, it's not easy to find the lecture numbers. So I scroll up and down, trying to find the right one. And then, once I latch onto it, I just watch them.
Right. Yeah, maybe for the people who do this course next time, we could make a nice little sheet with all the indexes and everything.
Yeah, one other thing that would be really helpful is if folks can make notes. So the DL PyTorch one, those were actually his class students making notes. So they had like 130 people making notes. And then they took all the 130 and merged it into one thing for the next incoming batch. So that was quite cool. I don't think we can do something around that scale though. I mean, but it's
Yeah, we could just have a Google Doc, which
right.
is week by week with notes, I guess, right? Yeah,
Right. Yeah.
nice.
Yeah. Okay. So this is probably not. Keep going forward, I guess. So this is learning objective. This is different though. I mean, this I don't remember seeing this.
I think it gets to the slide where it's talking about how you can't predict a graph. I remember looking at this one just a few yeah, this stuff here, right? Isn't that what you were just mentioning? That you
Yes, I remember this image. Okay. Yeah. So he said, he's talking about expressivity basically, right? So how would you define the nodes in a perfect or how would you define a perfect graph? So this is one way to do it. Basically, you create a k-hop neighborhood structure, and then kind of encode it as a vector. So
what's his definition of perfect? That you can predict the graph from the encoded GNN? I'm not sure what they mean by perfect exactly.
I think the ability to go, from graph to the vector or the matrix form without losing too much information.
Right.
I guess this is what he means by perfect. Maybe.
Yeah.
Yeah, I wasn't sure what injective function means.
One-on-one, if I remember correctly, surjective or something. I forgot.
Look it up. There we go. I was just going to do the same thing.
Okay.
Yeah, it's a one-on-one function. Okay,
right.
That's right. So basically, there is one thing corresponding to each part. So injective function between neighborhood structure and node embeddings. So yeah, so like individual node embeddings for the neighborhood structures.
Right.
Okay.
So basically what I got out of it was that, if you have a graph and you want to make node features, these are like really nice features that you can make, right? So, that was my take home. So,
right.
Yeah. So, yeah. So this is basically, so again, this is the observation we're talking about. So he says, okay, V1 and V2, if you just go with the edge structure that it has, there is no difference, right? But they could be V1 and V1 and V3 are actually different because they are part of different graphs, different looking graphs. So, what is the solution, right? So that's, he's just setting up the problem here.
Yeah, basically same as in injective function one-on-one. This is the
exactly.
same
Right.
Okay, I guess it's downloaded. Yeah, okay, it's okay.
Yeah, so he goes back to the WL test. I think we've learned about the WL test somewhere in lecture 5 or something. So
even the two. Okay. So should I move next to next slide?
I'm just going through it like really fast. So
yeah,
okay.
Definitely.
So more expressive than identity aware. So one of the methods he's talking about, two methods. One is position aware and one is identity aware. So I think if you show me the picture, then I'll remember. Otherwise, I don't actually remember what they are.
Okay. The previous slide or next slide?
No, previous. Sorry, next. Sorry, yeah. No, so position aware. What is position aware? Okay, so let's go on.
Something related to this. So these are the. Okay, I'll go to next slide then. Okay.
Yeah. Two different inputs are labeled differently. A failed module. Okay. So. Okay, different embeddings to V1 and V2. Okay, so let's go to the next one. One hot encoding. Okay, so that is a naive solution, and then he sets it up and then he knocks it down in the next slide, I guess. Okay, not scalable. Okay, right. That makes sense. And Yeah, because your population of nodes is like fixed, right? So you don't
Yeah,
know what
exactly.
it
We
means.
cannot add more nodes and
Right.
give embeddings to them.
Right.
So
So
that
now, okay. So he's got two of these, position aware and structure aware. So structural roles. So I think, the V2 is a betweenness kind of thing. And these are edge nodes, A's. The A's are edge nodes and B are kind of internal nodes. And
so sorry, like what will be the difference between structure and position aware? It might have been covered in previous lecture, but I just bit idea that so that I am able to understand what they're trying to say.
I think it's here he's saying like, what are the edge nodes, right? What are the nodes that connect these two subgraphs, right? Whereas here they're saying position. So you see two subgraphs in this graph. And so position aware would mark all the nodes in one subgraph as one type and the other as another type. Whereas structure aware will differentiate between the function of the nodes in the graph.
So,
right?
what do you mean by function? Like B is a kind of gateway node and A is...
Yes, structural roles, he says, right? So basically, so you can kind of look at this graph and say there are two subgraphs here, right? Connected by one big edge, right? This edge in the center.
Oh, okay. So that's why he's labeling these two as B while these are A.
Yes. Yeah.
And because they have different structure compared to these. These are some sort of a pathway nodes. If I
exactly, these are the bridge nodes, right? A bridge or between, and these are the A nodes. The edge, basically non-between nodes, right?
Non-between. And position aware means like it's in this, whether it's in this part
this
of the graph
exactly.
or this
Right,
part of
right,
the graph.
right.
So that's why A. Oh, understood. Thanks. So yeah, okay. GM for work for structure aware graphs.
Is there a way from an adjacency matrix to figure out things like bridge nodes? I think the positional aware you can easily get from an adjacency matrix because they're kind of close to each other.
Yes.
But things like, I'm not sure what other types of structural roles there are. So bridge node is obviously one. Not sure what else there was for structural roles, but
yeah, I don't actually know. I mean,
starting node might be one, like one of those head nodes, or like super connectors that are kind of...
well, super connectors are high betweenness, right?
Yeah.
I mean, so I think it's basically between and non-between in this case. This is, I think it's kind of a contrived example, maybe. So okay. So one of the things that these nodes have is that a lot of paths will go through it, right? Because anytime you want to go from A on the left corner to A on the right corner, you have to go through V2, the two Bs, right?
Right.
So that would be like, some kind of structural difference also. I don't know, so.
Yeah. Okay.
And so then he says GNNs do well with structure aware tasks because of this, dependence that you have to go through it, but it actually doesn't do very well on position aware because they don't differentiate, right? So then he says, that's the next question, and then he goes to the position aware embeddings.
Okay, what is the intuition behind like why GNNs will fail for position aware? Trying to basically...
I think because GNNs try to pool things, right? So they don't actually look at structural differences that well. I mean, they would tend to think of so when they look at the left triangle and the right triangle, right? They find that these are basically symmetrical, right? So they don't. So V1 and V2 will always have the same computation graph.
Yeah.
That is true. Yes, that is true. Right? Because if you just look at them, they're kind of identical. Although I would say that I would say they're isomorphic too, right? Right. If you think of this one and the A's and the B's, right, separately, they are exactly the same graphs. So they should have the same computational graphs. But yeah. Or maybe he's saying that he should be able to distinguish V1 and V2. Oh, I think that was one of the points he mentioned. So the point he talked about, sorry, go ahead, Wendy.
Yeah, so kind of, I think it's not, it's like, as you pointed out, because they are exactly the same, if you kind of split up like in the bottom diagram, then if you need to separate, say V1 and V2 are two different kind of nodes that you need to classify, then you can't actually do it.
Yeah.
But
Yeah.
Okay.
Yeah, I think the example he came up with was, this is something that he talked about very early in the class as well. So he says, like, if you have nodes 1, 2, 3, 4, and then you change the order of the nodes, maybe, you say 3, 1, 2, 4, right? Does the graph change, or does the representation of the vector change, right? Because the graph doesn't change, obviously, just you have the nodes in different order. But the representation of the vector, the adjacency matrix would change, right? So, yeah, so I think that was what his motivating example was. And I think that's, it's kind of similar to what Wendy said, right? Yeah, and this is the case of the anchor nodes, where you basically randomly pick two, or here he says just pick one, right? And then you choose, relative distances with respect to the anchor, and that's your coordinate axis. Now you can actually have more than one anchor node, and that gives you a multidimensional multidimensional vector for each node.
So if you have multiple anchors, then we'll have a vector. We'll have values from each anchor node, like distance from each anchor node.
From each node to each anchor node, yes.
Okay, so it will be if I have two anchor nodes, so it will be maybe n into two-dimensional matrix for this, right?
Yes.
Okay.
So here you can think of V1. See, okay, the next slide tells you, right, exactly the same thing. Go to the next slide, you'll see it.
Oh,
yeah.
Okay, cool.
Yeah. So each row is basically a vector, and it corresponds to each node, right? Here, the V1 node has vector 1, 2, and V2 has 2, 1. And so that's how they're different. So,
S1 and S2 are anchors, which are represented in the columns there.
Yeah.
Yeah. Okay, cool.
Welcome everyone to the class.
Yeah.
So you are then including those anchor nodes twice. Are you not in the embedding? You're including the anchors for each subgraph, but maybe that doesn't matter.
He basically said you pick randomly, pick a bunch of nodes randomly throughout the graph, and then calculate the distances.
Right.
So, yeah. I guess it so happens that the anchor nodes he chose were, nice. Then there is also anchor sets, right? So now he says, so why, okay, I think a single node defined distance anchor set, the minimum distance to all nodes in the anchor set. So you basically say for V1, what's the distance to, so assuming an anchor set of V3 and S1, you find the minimum distance from V1 to any of the nodes here, and you use that instead, right? So here it's 1, it's not much different. But here it might be for S2, for instance, it's only distance 1 to S1 and distance 2 to V3, but you only choose 1 here because you want the minimum distance. Or you could go up like this: S2, S1, V1, V3, right? But you still choose just 1, right? So, and you can save the total number of anchors. I don't remember what the benefit of this was, but if you go to the next slide, maybe you'll see it. Represents node in randomly anchor sets. Each dimensional position encoding is tied to an anchor set. Okay. Well, doesn't actually, but maybe it it gives you slight benefits. I think he talks about it, but I don't remember what it is.
So are you talking about like why we are taking total large number of anchor sets?
Yes. Well, no, why anchor sets versus anchors, right?
Okay. Okay.
I think he mentioned it somewhere about position correspondent augmented node feature. Here. So this is where he talks about, the positional encodings are invariant with respect to your, the node position. So it says dimensions of positional encoding can be randomly permuted without changing its meaning, because you're basically saying that, okay, it's a distance from the other nodes, right? It's a vector kind of saying that here is where the node is in relation to the others. So,
So dimensions of position encoding can be randomly permuted without changing its meaning. But then how would we know like which distance it refers to if we are randomly permuting it?
no, so you basically say that if you change, okay, go back one.
Okay.
Yeah. So if you change the position of S2 and S1, right, interchange, all of the features will change for each of these V1 and V3.
Okay, understood.
Right. Yeah. So, and basically you're saying that it's not tied to a particular node. It's because the node is now represented as a distance to various random nodes in the graph, right? So in that sense, I thought of it was, it was a nice feature, right, that you can use for graphs rather than, so it kind of tells you where it is kind of in relation with other nodes.
So it's saying that we don't need to fix the order of the nodes, you're saying. So if
yes,
you are permuting, we are exchanging this, the order will change, but otherwise we can still differentiate between in V1 and V3.
Yes, exactly.
Yeah.
Rigorous solution. Okay. Especially maintain the permutation invariant property of position encoding. Yeah, okay.
Okay, moving on.
Moving on. Yeah.
Yep.
Okay, identity aware. This is GNNs would fail for position aware tasks. Okay. Same number of failure cases. Can you go back one? Let's see. Node level. Okay, never mind. Okay, go forward again. Sorry. Example input graphs. Okay. So this we already saw before, right? No.
Yeah, like V1 and V2, and but that was specific to position, right? So here he's talking about structure aware tasks. So he's saying about V1 and V2 both have two neighbors, and we'll see their graph structure will be very similar.
Yeah.
Even though it is a three, it's a triangular and it's a, maybe I should say quadrilateral graph, just saying that.
Yeah.
So we won't be able to distinguish between using this GNN structure.
Right. I think that's because GNN looks at like, immediate neighbors followed by the next immediate neighbors and so on, right?
The aggregation part from that.
Yeah. So here it's got two neighbors and, so it's got two neighbors here. And then I think if you go further, I don't know how to go further on this. Maybe, yeah. So, okay, different inputs for the same. So he's giving you all these failure cases, edge cases that he comes up with.
Yeah, this was node level, then edge level. I guess this is the edge level. So V1 and V2 have both A and B share the node V0 left to the embeddings of V1 and V2. Okay, this I don't understand this. So what is this dotted line? Is it there or is it not there? So is it?
So he's saying consider edge A and consider edge V, right? So V0, V1 and V0, V2, these are the two edges. And then look at the embeddings for V1 and V2, just, based on this. So V1 connects to, 1, 2, 3 nodes here. Or how do you actually connect to 3 nodes?
So V1 is connected to this and this, and V2 is connected to, okay, sorry.
Oh, I see. Okay. So he's, okay, maybe these edges don't exist, or how do you get to A, right? So maybe V1 goes to here and then down here. Each of these are connected. Oh, okay. No, I think I got it. Here. So V1 goes to the left, right? Left node. That's the first one. So V1 can go to either the left node or V2. So these are the two, the immediate children, right? And then the next layer from the unnamed node in the corner down to V0, and then it can go back to V1. So hence you have another one here. And then you have another one here, and then it goes from V2. And now it can go back to, now from V2, you can go back to V0 or the unnamed node on the right. So the two levels are same. And if you now do the same thing with V2, so V2 has V1 on the left and unnamed node on the right. And then on the next layer, V1 will have V0 and the node on the right. So you have on the left this one. And now on this side, it should have another one. And that's where I'm not getting it, maybe. Okay. Yeah, so these are basically examples. I didn't think too much of it, so if he's saying it's a failure case, I accept it. So, so basically go on to the next thing here. What is the solution to it, right? So, oh, this is the coloring one. This is actually quite a neat one. So he says, like, just assign a color or assign a property, some property to each of the nodes, and you check for that. So as you create your computational graph, you can check for the propagation of this property, down as it gets more and more neighbors. You can see who the neighbors are, and then you'll find that the nodes in isomorphic graphs will have the same color structure. So if you go to the next slide, I think you'll do it with a square, and then you'll find it different here. Okay, permute the node ordering between V2 and V3. So V2 and V3, you just switched it around, but you still have the same. So that is one, invariant to node ordering. And I think he will do another one where it should be different.
So we think these two graphs are basically similar.
But the nodes order of the nodes V2 and V3 have changed, right? They're now flipped. Basically, it's like a reflection kind of thing around V1.
Yeah. But the computational graph stays the same because the connections are basically same.
Yes.
Now looking at this.
Yeah, now he's doing a square, and he will show that even though previously when in the uncolored situation, these two graphs are the same, but now that you have introduced the color attribute, right, you can now distinguish between these two guys.
Just a thought there, like thinking. So initially, if you're assuming that all the nodes were very similar, then we are not able to find the difference. Now we have introduced this color here. It means we are able to differentiate this node from other nodes. So that's what exactly he is doing, right?
That's all he's doing, and he's basically coloring one node, and that's it, right? So he takes one arbitrary node and then he just.
So is this specific thing like which node should we color, or is it a very general thing? We can.
I think it's a general thing.
Node.
Yeah, it's just select one, color it, and then draw the graph, and check for the graph difference.
In all the cases, the root node is colored. You see, like V1 and V2.
Right. Yeah. Although, I mean, the root node is kind of, our bias as well, right? It just happens on the left top corner. So, it could be somewhere else. I mean, you flip the graph, it's on the bottom now, right?
So, but we start with the root node. Is it like when we're trying to make the computational graph, we're trying to make it move from here?
Well, I mean, for a general computation graph, you start with all the nodes, right? But you're basically, he's taking the case of one node, and then he's, creating the DAG basically out of this, right? So, and then he's comparing the two DAGs.
Basically, at least one of the one of these cases will have a difference which will help us in identifying they are not the same.
Yes.
Okay. Again here, same thing, I guess. It's the same idea is propagated.
Yeah.
This one I'm still not clear. The link part one and the edge one. I think this is the one which is giving me trouble. Anyway, so again here it's like very similar. We have differences in the computational graph, right?
Right. Yeah.
Okay.
Yeah, so this is the, how do you do the heterogeneous message passing? Okay. Same message aggregation to each node. Okay, can you go to the next one? Okay. now different colors. Okay, so the idea is that you just have some different aggregation thing to nodes with different color. So maybe he'll tell you what the aggregation is next slide. Maybe. I see. Okay. So basically, he's saying that where you are doing the node embedding, right? So if you remember in the GNNs, you first take the X value, right, and you pass it through some kind of embedding for itself, and then you send it to the propagate thing, which sends it to all the neighbors where all get embedded, and then they aggregate and come back to you, right? So, so here he's saying that depending on the color of the node, so you check the attribute as it comes in, and you pass it through a different embedding layer, right? So you have two different embeddings for one with color and one without color, and so that way you'll be able to distinguish. So that is the idea here. Yeah, this is actually good because I didn't actually catch this idea last time. Yeah. Okay.
So, okay. So is it equal to -1 length minus, okay, no, cycles is equal to 2. Okay. So basically here he's able to calculate the cycle length, I guess.
Yeah. And that's the intuition behind the IDGNN fast, right? Instead of just looking at, so no need to do heterogeneous message passing anyway now. He just says use the cycle counts in each layer as an augmented node feature. Not sure how this will work, but okay.
So what is saying, like length 3, if you because it is of length 4, is it that's why the cycle is 0, but right now here it is length cycles are 2. I'm not sure. Follow this.
Maybe go to the previous one and see what's going on here. Okay. Why does IDGNN work? So we know this, right? Okay. Oh, intuition. IDGNN can count cycles originating from a given node, but GNN cannot. Okay. Because
That's
it can,
because of its
because of
coloring
color.
part.
Right.
So it will be able to track like how this basically this message is coming back to itself.
Right. So here it's like 1, 2. So cycle length will be 2. And here, if it comes from V1 to the left one, and then the colored one, no, not the colored one, the right one, and then the colored one. So it will be 1, 2, 3, right? So maybe that's the intuition here. Can we go to the next one and see if that tracks? Yeah, it tells you here, right? So cycle count at each level. So it's 1. Then at the second level, there is no way to reach V1, so it's 0. Then third level, you have reached back to yourself, so it's now cycle count is 2 edges. And then on the fourth level, there is a way to come back here. So 1, 2, 3, but why is it 2? Length 3 cycles. Oh, how many cycles? Okay, how many times were you able to get in here? Right. So here, sorry, so this number is basically the number of times you see the colored thing in this level, right? So it's 1
so
here.
How many number of times you were able to come back, as you were saying.
Right.
So first is basically you are there itself, so it is always 1.
Right.
And 0 is like you move to this or this node, or here you reach or this node.
Right.
In this part, it's like either 1, 2, 1, 2, 2. I mean, there are 2 ways you can come back. So there will be 2.
Right.
And in the third, you can do 1, 2, 3. So you can come back using this thing. But here, because it's 4 edges, so
you cannot come back. Yeah.
It will need so
one more. Yeah.
2. Yeah, it will need 1 more cycle coming back. Okay. So that will tell you the number of the cycle length.
Correct. Yeah. So you can use that as your augmented node feature instead of having to do this two separate embeddings thing.
Okay, so this is the total number of nodes won't tell you the cycle length, but what is the minimum possible case when you are able to come back. So here you're able to come back at 3. Okay.
Yeah, well, the length 3, it basically corresponds to the third layer, right? So, you know, if you think of the any GNN layer, it basically says, okay, you know, the first layer will take care of all your neighbors. The next layer will take care of your neighbors' neighbors. The next care of the neighbors' neighbors, and so on, right? Right. So that will basically give you the, you know, the length bit, right? And then you can basically count how many times you have seen in your batch, right? How many times you have seen this colored thing. So that will give you the number of cycles.
Yeah, understood. So but I have this question, like in case this is broken, I don't have this point, I have only 2 edges there, then would I be able to distinguish? Because the cases in that, if I have computational graph of that, I'll have all whites here, and only on the even number side, even number, if I consider this one, it 0, 1, 2, 3, only on 4th and 6th and 8th I'll have this color thing there. So would I be able to understand whether this is a whole cycle or it's just a open cycle with one or an even odd size length branching?
Okay. Yeah. Well, I mean, how will you know this cycle? But cycles will only happen, right? So cycles will only happen for closed graphs, right? So in case this bottom thing was gone, right, for the square graph, then you wouldn't actually be able to go beyond the first layer, right? Because you cannot come back from there.
Okay.
So yeah. So identity IDGNN is there. So that is another one. And I think that's pretty much all it is. He says, you know, this is a small change to either of them. I guess with the IDGNN, it should be easy. With cycle thing, it should also be, I guess, easy. So, you know, but I haven't done either, you know, either change. So, but I can see how this will be not that hard to do, and it's consistent performance gain. So that's nice. Okay. Impressive performance. Yeah. So this, he goes on these adversarial examples, and that goes more into, you know, non-graphy things here. So.
Okay, talking about adversarial attacks, how about GNN? Okay, how robust are they? Input class.
Oh, here. Okay, now I remember now. So basically, they're saying that, you know, you can poison these graphs strategically to get different results, right? So semi-supervised node classification. So he takes an example, predict labels of unlabeled nodes, right? And then keep going, and then I think he will give you a real world GCN model. Okay. So those label prediction we want to change. Attack. Okay, modify target node feature, change website content. So these are ways in which you can basically do the poisoning, right? Attacking, removing, you know, connections and.
Okay, modify target node feature, modify attacker node feature. Okay.
Yeah, some of these are, you know, fairly well known, like link farms. Google already, you know, downgrades them whenever you see a, you know, link farms are basically, you know, you have a bunch of links and you're hoping to get all the, you know, the click goodness from the other ones or the ones you link to, but it usually works the other way. So PageRank will automatically downgrade you. Also, Google basically goes and, you know, will penalize you for creating link farms anyway. So anyway. but otherwise, others ones are like a little bit harder, I think. And then here, I think he talks about
change the target node label prediction. Okay.
yeah, I didn't actually pay much attention to this because this wasn't very, yeah. But we can. Okay.
Basically saying if you have like your modification is very small, you won't be able to detect it, something like that. Okay, target node, then GC node. Okay, so basically with very small modification, we want the prediction to change due to based on manipulation. That's what I'm unable to understand.
Yes, I think that's correct. Yeah. Yeah, I think he trains something. This is like a loss function, and then he will try to train something using this, if I remember correctly. Yeah. So.
Okay. Moving on.
Yeah.
What does it say? Semi-supervised node classification GCN on a paper citation network. Correct, incorrect.
Yeah, so this is like a clean graph where most of the things are in class 6. And oh no, wait, class 6, correct.
Yeah, this is prior to the adversarial attacks,
right.
And this is after the adversarial attacks. Goes to everything goes to class 7, almost everything.
Right.
Confidently makes wrong predictions. GCN performance compared to no attack. Random attack is weaker, much weaker than adversarial attack. It is more challenging than a direct attack. Okay. So this is adversarial direct attack. Is this misclassification, right? Oh yeah, misclassification.
Yes. Yeah.
Okay. I think this is a motivation for the next
Basically,
lecture.
the takeaway from here, yeah, it's not robust, but somewhat robust to indirect and random.
Oh, nice. I think we had a very good overview. Thanks. You want me to open this the
17? Yeah, sure. Let's do that. I mean, I typically don't, like I said, I don't go into very much detail because of speed issues also, right? Because we are moving very fast here. So
True,
essentially, I want to find out where everything is so that when I actually need it, I'll come back to it. So yeah. This is
like application thing.
Yeah, this is scaling. I think there's more to do with scaling. This one.
Okay.
But anyway, let's keep going. Social networks. Yeah, these are just motivating things he's talking about. Wikidata. Okay. Scale up GNNs to large graphs. Okay.
I was reading a little bit like in the early days, we were trying to pick between their Snap library and the Network X.
Mm-hmm.
So I guess Network X is 100% in Python. So that's why people don't use it for these bigger projects. But there's another thing called, I think, Graph Tool, which seems to be a popular library that's all written in like C++ templates.
Okay. And if you have GPUs, you can also use CU Graph. So it's on it's basically Network X like, but they have a backend that is NVIDIA. It basically works against NVIDIA's GPUs.
Got it.
What's the name of that?
CU Graph. So
CU.
if you CU one word, CU Graph. Yeah, there you go. This one. It's fine.
I think you had mentioned in the previous someone of them.
This is part of the Rapid suite. So they have like CUDF, which is like pandas like on GPU, and I think CU Pi, which is NumPy on GPU, and this one.
Hmm.
Oh, CUML as well, which is like a subset of scikit-learn on GPU.
Okay, so he's talking about stochastic gradient descent, etc. And this is very general ML stuff.
SGD is some kind of sigmoid descent, or what does SGD?
Stochastic.
Stochastic gradient descent.
Okay.
It is like one of the earliest, optimizing. Yeah. Well, actually, sorry, my bad. It is basically gradient descent, but batched, right? Batched,
Okay.
Yeah,
and it starts from random, I think. Yeah.
Yeah, right, exactly. So it takes just a small sample and randoms a single observation into account to calculate the gradient. So it's a pretty noisy, but over time it reaches the zenith pretty fast compared to the if you're going to calculate gradient over whole data set. So okay, so he tells like GNN cannot standard standard SGD cannot effectively train GNNs because the sample nodes tend to be isolated from each other. So maybe they're not able to capture the whole structure. GNN generate node embeddings by aggregating neighborhood node features. Okay, and because they're isolated, then it does not have access to neighboring nodes within the mini batch. Okay, that's what I understand here.
Yeah, I think that's correct. Yeah.
So live full batch implementation. Generate the embeddings of all nodes at the same time, load the entire graph and features at each GNN embedding, compute embeddings of all nodes, compute the perform gradient descent. So how is it different from normal gradient descent?
Oh, because you're doing the full batch, right? You're loading the entire graph. So then you have access to all the nodes, right? You're not, you're not losing edges because of sampling.
Yeah, so it's basically normal gradient descent, your full gradient descent.
Exactly, right.
Okay. It's not feasible. React makes sense. It's not feasible for large graphs. 3 methods for scaling of the GNN: neighborhood sampling, cluster GCN, and simplified GCN.
Yeah. So these are the 3 things we'll talk about in the lecture.
Okay. Okay. So basically, it's a repetition of what we had learned, like how it aggregates, right? So observation: k-layered GNN generate embeddings of a node using k-hop neighborhood structure and features. Okay. To compute neighbor embedding of a single node, all we need is a k-hop neighborhood. Okay. So given a supreme different nodes in a mini batch, we can generate their embeddings using M computational graphs chemical in GPU.
So he's basically using, he's generating these graphs dynamically, right? And he's saying that, for each of them, if you get the k-hop neighborhood, that defines the graph adequately, or defines the node adequately enough, right? So
for calculating the gradients, because we only need this k after k-hop, whatever the neighborhoods are there, only we need only those, not more.
It's an approximation. I think it's similar to, when you do the Markov assumption, right? You say, okay, I just care about the previous word, right? Or the previous 3 words, right? Those are the ones that determine this kind of word. So I think it's kind of an approximation here as well.
Yeah, so I don't need any like other nodes which are outside this k-hop jumps.
Exactly, right.
So we randomly sample n nodes. For each sample week, we do k-hop neighborhood, and we consider the computational graph. As you said, like we do generate M computational graph based on M nodes. Then we use above to generate V embeddings for specific node V. Then we average the loss over M nodes. We perform SGD on that sample.
Yeah. So at this point, you have got over the sampling loss, losing the edges problem, right? Because of sampling.
Right. Because it's not a random sampling we are doing. We are doing some sort of a smart sampling
Yes,
by
yeah.
using this graph structure
Yeah.
to figure out which nodes we need.
Right.
Okay. So for each node, we need to get the entire key of neighborhood and pass it to the computational graph. Okay. We need to aggregate a lot of information just to compute one node embedding, which is computationally expensive. Yes, okay. It becomes exponentially large with respect to layer size k. It explodes when it hits a hub node, high degree node, make computational graph more. Okay. At most edge neighbors. I think we had this idea somewhere in the one of the previous lectures also. Like instead of trying to calculate from everyone, we take a random sample on each layer. So
yes, I remember this. Yeah, you're right.
Yeah, right.
Yeah.
So he was giving example of Kardashians or something like that.
Right. Yeah.
Okay, so this one we take some sample. So I guess at each layer we're taking some sample, something like that. So first top neighborhood, second top neighborhood, first sample 2 and 3. Okay, we take and for this layer it takes just these two 0, 8 and 8, 9. Here he is dropping 0, 0, 4, 6, and 7. We can prune computational graph to more efficiently compute. So what he's doing, I understand, is he's introducing more noise, although, but the computational time will reduce considerably.
Right.
It's very similar to what the SGD does. Okay, neighborhood samples for KNN for each, sir. Okay, this is basically the algorithm he's put in points. Trade-off in sampling, a smaller edge leads to more efficient neighborhood aggregation, but results be more unstable, basically more noise due to larger variance in neighborhood aggregation. Computational time will reduce. Size of the computational graph is still exponentially with respect to number of layers. Makes sense. Interesting. Increasing one GNL will make computational edge times more expensive. Makes sense. How to sample the nodes? Random sampling. Random walk with restarts. Okay. So what is he doing here? Like he samples the low degree leaf nodes. Samples many low degree leaf nodes.
So you start, say, at the green node, right?
Okay.
Each level you sample H with the highest RI. RI is the restart score. Random walk with restart score RI starting in the green node. So I think he's doing something similar with the. So he maybe like PageRank, I think, right? I mean, you start doing a random walk and then with some probability you start back, right? So it's like personalized PageRank almost, right? Coming back to the same node and do it again. Yeah, and doing again.
So compute random walk with restart score RI starting at green nodes with some probability, and at each level edge neighbors I with highest RI. This strategy was so, okay. I have not understood it intuitively. I don't know how it works. So we create computational graph constructed for each node in mini batch. It's very similar to the previous technique. Neighborhood sampling, the computational graph is pruned to increase computational. Pruned computational graph is used to generate a node embedding. So the computational graph can still become large, especially for GNN with many message passing layers. Okay. The size of computational graph becomes exponentially large with respect to layers. Computation is redundant when nodes in mini batch share many layers. Okay, what does this mean?
So I think when you're doing in this particular situation, right? If you look at the A and B on the right, basically the computation for C and D are repeated, right? Even though I think it will lead to some kind of dynamic programming situation where, so, when you're trying to compute A, the embedding for A, you're getting, you have to compute the embedding for C and D. Again, when you want to compute embedding for B, you again have to compute C and D. So
okay.
yeah, so I think you can cache them somewhere, right? So
right, yeah, makes sense. So just calculate once and just use it multiple times.
Right, yeah.
Okay, full batch linear implementation. All the node embeddings are updated together using embeddings of previous layer. Okay, this is what we have already know. In each layer, only 2 edges message are needed to be computed. For clear, only 2K edges message need to be computed. So is this based on the sampling of just 2 layers or 2 neighborhoods or something? Because he's saying 2K number of layers messages need to be computed, something like that. I'm not sure how this 2 number is coming.
The number of edges, twice the number of edges. Why twice? Each layer twice the number of edges. Messages.
Oh, 2 messages. So this one is one message and this one is one.
Oh,
message.
they itself and okay. The X itself and all the neighbors of X, right? Yeah,
Yeah.
okay.
So GNN's entire computation is only linear in edges and GNN layers. Okay, I don't understand because this, so it's by itself it is fine, but the second part it's aggregating from others. So I don't know
Yeah.
how this arithmetic is 2.
But that is in parallel. So I guess that's what he is talking about, right? So from a point of view of computation, you basically go to all its neighbors and then you add them, right? Messages need to be computed. I think maybe because of that. No, why is it 2 times the number of edges then? That's the question, right? Oh, it's going back and forth. I see. So look at the bottom picture.
Yeah, this one, right?
Right. Yeah. So the first, it basically sends out each node sends out signals to all its neighbors, and at each node, it aggregates the signals that are incoming from all its neighbors. So hence the 2, so the broadcast is the first N, right? And the aggregation is the second N.
Oh, okay. What I understood, like I'm not sure. So this could be correct. Might be correct. What I have understood, like instead of looking at nodes, we have to just look at edges, as you were mentioning, right?
Mhm.
So there is information going from left to right and from right to left.
Yes.
So that will tell us like how many times messages have to be passed, irrespective of nodes.
Exactly. Right.
So after caching, as you were mentioning, we have to just calculate it for 2 into number of edges. Because the sharing part.
I see. Okay. Maybe we got it. Okay. Yeah. Okay.
So if I calculate this, I can use this for both A and B, right?
Mhm.
So I have to
Yes.
calculate it only once for this edge and once for this edge.
Yes.
I can repeat those. The calculations can be reused.
Mhm. Yeah.
The layer-wise node embeddings.
Reuse. Okay. Right.
Use of embeddings from previous layer. Okay, the significant reduce the computational redundancy. So yeah, it's all still on, for me, it's all still on shaky ground, but I guess that could be the whole idea.
Right.
The layer-wise update is not feasible for large graph due to limitation of GPU memory. Okay, we can sample a small subgraph of large graph and then perform the efficient layer-wise embeddings update over the subgraphs. So talks about the subgraphs. JNN performs node embedding by passing messages via the edges. Subgraphs should retain edge connectivity structure of the original graph as much as possible. Okay, that makes sense. The JNN over subgraph generates embedding closer to JNN's over original graph. Okay, so this versus this. Left subgraph retains the essential community structure among 4 nodes. Good. Right subgraph drops many connectivity patterns, even leading to isolated nodes. That's why it is bad. Real world graph exhibits community structure. A large subgraph can be decomposed into many small communities. Small community as a subgraph. Okay, so basically these are the 3 subgraphs which would be optimal for this case to preserve the local connectivity patterns. So we first introduced the vanilla cluster GCN. Cluster GCN consists of 2 steps: pre-processing and mini batch training. Partition into group of nodes, subgraphs basically, and sample one node group at each time. Node group means
This clusters.
The cluster. Apply GNN's message passing over induced subgraph. So here I split this into 3 parts and then do the message passing in each of the subgraphs.
Right.
And compute the loss. Given a subgraph, okay, this is basically putting those into lines. We can calculate any complete detection methods. VCS.
And I think this, it's kind of leveraging the structure that you see in nature. the fractal nature, right? I mean, where
Right.
you have a big pattern composed of small patterns will look like a big pattern, you know, and so on, right? So
Okay, for each mini batch, randomly sample node group VC. Okay, so is he also sampling among out of these also? So he's randomly sample a node group.
in this graph VC, well, yeah, I guess. Yeah, so he's randomly sampling a node group here, I guess. Yeah.
Okay, so basically it's a stochastic gradient descent at a
But can you
subgraph
go
level.
back? Can you go back to, he mentioned Louvain somewhere?
Yeah,
Yeah.
yeah.
Any scalable community detection method. So you have to break it up into C groups, and for within these each of these C groups, I think, right? So okay. So GC, VC, EC. Okay.
Sorry. Okay.
Yeah.
You want me to go to the next slide?
Yeah, please. Yeah. Okay,
So,
from here he's sampling a mini node group VC. Okay.
so that's what I was saying. Maybe it's what I understand. It's doing SGD at a subgraph level, taking first sample.
Yeah. I think although I mean, I think you might have to use some kind of smarter, you know, this randomly is probably not correct, I think, you know, or node group. Okay, never mind. Sorry. So you basically construct these, you know, subgraphs like using Louvain or some other clustering algorithm. And then from within that, you randomly sample a node group of VC. Okay.
Node group means like subgraph you mentioned, right?
Yes.
So this diagram is, I guess this diagram is pretty deceptive now. Sample
Yes.
node group VC. These edges exist already, right?
Exactly. Right. Yeah.
Yeah, and this is one of the subgraphs he was able to detect.
Yeah.
Okay. So yeah, so this is
this construct induced subgraph, you know, I think it's kind of redundant. Maybe you know, it's already constructed, or maybe he's using Louvain to just find the, you know, community vertices, and then, you know, using those community vertices, he says, okay, construct this VCEC.
so I was saying, is he adding edges to the
No,
induced
he's not adding edges. He's basically saying that, okay, I have a group of nodes VC that I found through Louvain or something else, right? And then using, you know, then I basically create this. I also have a corresponding EC, right? So, and I create my subgraph GC and move forward. So I think the left, you know, the picture is, yeah, it's
right.
kind of misleading, I think.
Yeah, that's why I was wondering, what does it mean by construct here?
Right.
So yeah. So layer-wise node update over GC to obtain embedding HV for each node. V of VC, that's selected subgraph.
Right.
Compute the loss for each node V of VC and take average. Okay. And we update parameters. So a sample of the parameters might be updated. Okay, so subgraph GC embeddings, this subgroup removes the induced subgraph removes in between group links.
Yes.
Okay, so these links, the gray ones, will be removed if I understand correctly.
Yes.
Yeah, lost messages. Okay, so messages are lost between message passing, which could hurt the GNN's performance. So graph unity detection algorithm put similar nodes together in the same groups. Sample node groups tend to cover only the small concentrated portion of the entire area. Basically, that is the subgraph. Sample nodes are not diverse enough to represent the entire graph structure. Okay. As a result, the gradient averaged over the sampled nodes VC, which is a part of V, which is part of VC, becomes unreliable. It fluctuates a lot from one node group to another. In others, the gradient has high variance. It's the slow convergence of SGD. Okay. What is solution? The solution is to aggregate multiple node groups per mini batch. Okay. Basically, instead of doing for one, maybe two for more, partition the graph into relatively small groups of nodes. For each mini batch, sample and aggregate multiple node groups. Okay. So instead of taking one node group, he's aggregating multiple node groups.
Yes.
Construct the induced subgraph of the aggregated node group. Okay, a subsample made up of subgraphs which are connected to each other. Otherwise, it is similar.
Right.
Okay, so he's taking these two, for example, and he's creating this, and he's doing the aggregation over this. makes sample nodes more representative of entire nodes, leads to less variance among ingredient estimation. So includes between edges, messages can flow across groups. Okay, similar to where in the cluster in GC, and once it's pre-processing steps, partition into C relatively small groups. V to VC needs to be small so that even if the multiple of them gets aggregated, the resulting group would not be too large. Okay, each of these should be small, right?
Right.
So
But because you're doing multiple, you now take the edges between the small clusters as well into consideration. So it's again approximation, but little better, I guess.
Yeah. So from SGD is like sort of a mini batch one.
Right.
So for each mini batch, randomly sample a set of Q node groups, which is a subset of V212 VC, and aggregate over across the sample node groups with aggregation is okay. I don't understand what is saying this.
Yeah. He's basically taking the union of nodes, right? Although here they're disjoint unions, so it's really you could do plus and also get away with it. Right. So, and then he does an aggregated graph on top of
they might not be disjoint, or like if I'm taking a sample, so I'm preserving the links between the selected ones too. So they are not might not be exactly disjoint. So there's a message passing between these two.
Okay, but the vertex set would be, the left triangle and the right triangle, right? I mean, would it have this edge between them? Maybe it would have.
Yeah, so he mentions, right, it includes between group edges and messages can go across groups.
Okay.
So that's why I think the plus won't work, right?
Okay, yeah, probably, yeah. So it's a union. I mean, common things are, subsumed, right? So it's okay.
Okay, so we can aggregate them and consider as a single subgraph, like
exactly.
of all the Q1. So extract the induced subgraph, which is aggregation and aggregation of V aggregated and E aggregated, where this. Okay, so yeah, he mentioned this that that aggregator includes the between group edges too. Right. So M nodes embeddings using K-layer GNN neighborhood sampling. Okay, so where are we now? Okay. Suddenly, I think what is he talking about?
Time complexity. So how?
Okay. Yeah. So for M nodes, the cost is M into HK. Okay. H nodes per layer for each node size of the K layer is HK. Okay. I guess you'll have to think about it, like how the calculation part. So K layer message passing over subgraph course at most K into M into D average. So D average being the average node degree. So M is the total number of nodes. K is the total number of.
So this is the original, right? I mean, the first one, where he has the power of K. So essentially, you are creating for those initial embeddings, you have to have M of these nodes, right? And if you do K layers, then it's H to the power of K, right? Computational H nodes per layer if you sample, so H to the power K. Now compare it to the cluster one where you pre-cluster things. Now you're already thinking of you're doing subgraphs and you're no longer doing this previous the node embedding calculation. So now you can only do it in K, so K layers, so K times you have to do. And then M is the number of nodes, subgraph nodes, average, I guess. And D is the average node degree. So,
average node degree.
So this is much less than the K, H to the power K, whatever it was.
So this is also taking advantage of the fact that there are the calculations, edge calculations there, which are getting repeated across these nodes, which we are not taking into account.
Yes.
In summary, the cost to generate embeddings of N nodes using K layer is M to the power HK. Oh, basically same thing, assuming H is equal to D average by 2, 50% neighbors are sampled. So it's linear dependency with respect to K. That is the underlying. I think it's a repetition of the stuff what he was talking about.
Basically, he's telling you what it was.
Simplifying GNN, start with graph.
Yeah, this one is like removing nonlinear activation.
Mhm.
It's kind of, weird, I think. But I guess, if you're thinking of it as like, if it's just, you're aggregating the neighbors, and it's a simplified graph, basically. The interactions are much simpler. So
Just a linear aggregation. Then
yeah,
it would be,
yeah.
right? So given roughly with input features, E includes the self loop. I guess. Okay, this is aggregate neighbors information as summation with.
Yeah. So
Okay,
this is the
actual
standard GCN.
standard one. The ReLU is
Yes.
the non-linear. It could be anything
Yeah.
else. Non-linear.
Right. So your next layer value is always the ReLU of the aggregated value of the previous layers, right?
Right.
So instead of, now he removes the ReLU and says, okay, this is straight up, right? And it creates a much simpler, you don't have the nonlinearity. So then he can think of it in matrix terms, and he reformulates the problem here.
Okay.
I think of it, how Word2Vec and Glove are kind of the same thing, but they arrive at by different ways, right? Glove, it basically does a huge matrix factorization, and Word2Vec is basically just a two-layer neural network. And there, you can prove that one is identical to the other. So I think the same ideas are taken in here as well.
Okay, just okay. Ignoring math for now.
Well, so go back one. So
Yeah.
when he removes the ReLU, one more forward. Yeah, here at the bottom. So when he removes the ReLU, this basically becomes equivalent to this, the adjacency matrix times the matrix of the vector, the node vector, right?
Yeah.
And
I think
divided
it was
by
mentioned in the, yeah. Sorry.
divided by the diagonal matrix. So yeah. So
This
this
is
is
on
kind of
individual layers. We can put it in terms of a matrix.
exactly right.
That's what he has done. What I understand.
Yeah.
So you can basically multiply the whole agency matrix to the vector of all nodes. Matrix of all embeddings, linear embeddings,
Right.
divided by a. I think it's a diagonal matrix of the degree, the inverse of degree.
Right.
Right. So that will represent this whole idea here.
Yeah.
Yeah, exactly. So the matrix of hidden embedding. So that is H.
Right.
It's k-dimensional. Okay. Next, GCN's aggregation. What is he doing here? Okay, H WT. GCN is renormalized function. The ability to gives him better performance then. Okay. So what is happening here?
So he's basically now able to calculate this GCN using this under note, right? Whatever the curly on top, right? So you can now calculate it using matrix multiplication, basically.
Okay, now he removes. So instead of this ReLU, he's there directly taking this
right
H plus. So composition of linear transformation. You can put that as a single step, AK into WT. Removing ReLU significantly simplifies GCN. Yeah, because you are able to take the previous linear layers and just aggregate them as a single layer, right?
Yeah, exactly.
Not any learnable parameter since it can be pre-computed, right? Efficiently computable computed sequence of sparse matrix vector functions. So x is k times. Yeah. Okay. So okay, the pre-computed matrix simplified GCN's final embeddings, just linear transformation of pre-computed matrix back to node embedding form, pre-computed feature vector node v embedding own pre-processed feature. Okay, because there is no learnable parameter here.
Exactly.
So
this is just matrix multiplication, basically, right?
Yeah.
At this point.
So if once X hat is pre-computed, embeddings of M nodes can be generated in time linear in M. Okay. Understood. So in summary, simplified GCN consists of two steps: pre-processing step mini batch training step. What is the training part here? You're basically calculating it.
Yeah.
So
So what you have done,
yeah.
in the first step, all you have done is create node vectors. And in the second step, you're just using the node vectors to do some operation. Right. So there is no, this is like a regular, it's not a graph neural network anymore. Yeah. So let's say you want to do classification, right? You basically take these node vectors and you basically create a bunch of dense layers on the top, and you say, okay, final is like, is it good or bad or whatever, right? So whatever number of classes you have.
So why are we having this training part, and what does it mean by pre-compute processing step? So
So
as you mentioned, there is nothing to learn.
Yeah, there is nothing to learn, but what it learns basically is the graph structure. Or what, okay, it doesn't even learn it. It basically reflects it, right? Using these computations. Right, so it incorporates adjacency matrix into itself, and it creates a dense feature vector, right, for each node. And now for each node, you want to say predict something with it, right? So maybe some kind of node classification or something. So then,
what kind of
yeah.
This one is doing, as you mentioned, like perform SGD parameter updating. What kind of updation is doing now?
So now you want to, so let's say you want to have these nodes, and you're saying, okay, is this a disease or a drug node, right? But it doesn't know yet. It has basically incorporated all the features from its neighbors. Now it's up to you to take those features and teach some neural network that this set of features represents a drug versus a disease or whatever, right? And so then you have to train it. So these are essentially, it's basically a feature vectorizer, the first step, right? And then you have labeled data, and you say, okay, node V1 represents a drug, node V2 represents a disease, and so on, right? Label data. And then you basically train a set of weights that can read those node embeddings that you just calculated, and then predict whether it's this class or that class, or someone, like multi-class, some kind of thing.
Okay. So simplified GCN much more efficiently. No need to construct the giant computational graph. Mini batch nodes can be sampled completely randomly from the entire nodes. Okay. Okay, that makes sense. In semi-supervised node classification benchmark, simplified GCN works comparatively to the original GNN, despite being less expressive.
Okay.
Should I move next?
Yeah. Yeah, this is a important thing that he says, right? Why the this vectorizing part works, right? Because of homophily.
Okay, so because of the homophily structure, so
yes.
Two papers tend to share the same category. If one cites another, recommendations within social networks have a similar might be taste or so recall the pre-processing step of the simplified GCN, XAN for k times pre-processing features obtained by iteratively averaging their neighborhood features. Okay, the nodes connected by edges tend to have similar pre-processed features. Okay, so model uses pre-processed node features to make predictions. Nodes connected by edges tend to get similar pre-processed features. That's the whole idea, right? Homophily structure. Yeah, that is the reason of the so simplified GCN removes non-linearity in GCN and reduces to simple pre-processing of node features. Okay. Node classification benchmarks. Oh, okay. That is the last slide.
Yeah. There you go. So, yeah.
Thanks a lot.
Sure. It helped me a lot too to go through it twice. I mean, the second time, because I was, there's some parts I missed, and so yeah, absolutely. Thank you.
I think that makes sense to go through the whole like the chapters when we are talking. So sort of a revision for the person who have done, and if we have not done, like me, I've not gone through that chapter. So still I have get some overview of what is I'm going to expect.
Yeah.
So that was pretty helpful. Thanks a lot.
Cool. No problem. Thank you.
So do we have anything in an agenda, anything else in the agenda today?
David was making some notes here.
Yeah, I just started.
Okay. I see. Okay. Yeah. I see. Okay. Meeting recordings. Cool. All right.
But yeah, 3 lectures to go. Computational biology. Is that next week? I'll have to check the schedule.
Let's see. 16-1. Okay, let me find 18 maybe. 18. GNNs in computational biology. Yeah. This is just one lecture, I think, or
Right.
not, maybe. Yeah, it's just,
I think
and
too,
then,
that's kind of more what's the current state of research type of thing rather than new concepts. I mean, like, as how do I say it? So less sort of like teaching lecture and more kind of research seminar. Right?
More like applications that people are using it for in biology.
yeah, graphs are big in biology. Even the non-neural stuff, they use a lot of graphs even before that.
Right.
Pathfinding and things like that, link prediction.
Yeah, it looks like these slides are from Harvard. These are like a different set of slides.
So which one, David? 17.
Not 17 is what you just did, isn't it? I was looking at 18.
Sorry,
16 and 17, yeah.
I was looking at
18th one. I think the guest lecture, Gene from computational biology. So can you share the screen? I think, sir. Mine is
yeah, I just shared the link in the chat, but let me see if I can share a screen as well. Oops.
Okay. Yeah, you can see.
Slides. Yeah. So I just took that from, I just put this doc together. So 18 is taken from the course, and it's, the name is different. So Zipnik, I guess, is a different person. I think I saw some of the videos had other people as well, but I'm not sure. So yeah, biology is interconnected networks. Well, we don't want to.
It will be good to have some sort of application overview because it's been very theoretical till now, I guess.
Yeah. Are any of you in the biology or kind of drug pharmacy area? Is that crossover with anyone's work?
Not directly.
Right.
I'm not part of that team, but I know people who would probably benefit.
Right. But I mean, it is talking about aggregate neighbors and other types of ideas, I guess, that are specifically useful for biology applications. So it's not purely polypharmacy data set.
Yeah, polypharmacy is actually the area where one of my ex-colleagues is. He's actually working on that project. Basically, so if you have a person with multiple diseases, right? What are the medications that you're going to give him so that they don't stomp on each other and create problems for them? So that's what polypharmacy is.
Wow.
So, cool. Will it be possible for, maybe like I say it's a tall order, but will it be possible for like if we have some sort of a like overview of what is happening on that front, maybe like for a person who is working in that area and like using GraphNet?
I could ask him if you want to.
Yeah, definitely. I guess I would say that would be awesome.
Yeah, I can ask him.
I'm in financial space and fintech part, so I think it's being used in fintech part also a lot. I see some of the job openings which mention that they need some graph structure kind of data.
Yeah, it looks like they don't touch it here. Unfortunately, they just have industrial and science. I'd love it if you want to do a guest lecture on fintech applications. That would be interesting.
Definitely. I would be very much. I would be thrilled.
But what are you actually using it for? Is it like fraud detection stuff or?
No, I'm not using it. I basically want to use it for some good things.
Okay.
But nothing right now. So I was
Got it.
wondering whether someone can give us some sites or like what they're doing exactly, how they're approaching those problems. So that will be helpful instead of having a very cold start.
Yeah, well, I guess Dave, if you look above here in the Slack, his company is got acquired by Equifax, which is like the credit bureau, right? So that's kind of fintech related. Maybe he'll have some time. Maybe he'll come back next week. You could ask him, think about it. Give us some proprietary secret information here over our public Zoom link. It's only a $2 billion acquisition. Cool. Well, yeah, it looks like there's some interesting stuff here. Excellent. Well, I'm going to get on with some other stuff. So probably
Yep.
connect with you guys next week. Thanks a
Yeah.
lot.
Yeah. I think we can stop at this point.
Yeah.
Half an hour ahead, but still. Yeah. All right.
Okay.
Thank you, guys. All right.
Thank you.
Thanks, everybody. Bye.